Modeling with functions. Functions can be used to model a number of real-world situations. Here is a look at just a few ways functions can be applied to model situations and solve problems. For example 1, we're going to look at how we can work with formulas. Okay, we're going to write the area of a circle as a function of different variables. We're going to do that with the radius, with the diameter, and the circumference. Okay, now the very first, in terms of the radius, is the general formula that you're used to. Area as a function of radius is going to be equal to pi r squared. And that's it for that one. All right, for the diameter, what we're going to need to do is build a relationship between the diameter d and the radius r, because in the first equation, the r is the input variable. Okay, so the connection here is that the diameter is going to be equal to 2r. And if we solve for the radius, we would get that the radius is equal to d divided by 2. And the reason that we do that is because we've already got a template where we use the radius. So we can substitute in d over 2 for the radius here, and that will complete our formula. Okay, the area in terms of d is going to be equal to pi multiplied by the radius squared, but the radius is d over 2. So we get that. Okay, so you can clean this up a little bit. You can go ahead and realize that 2 to the second power is actually a 4. So we can move the divisor of the 4 out front. And we get pi over 4 times d squared. For the circumference is equal to 2 pi r. That would lead us to having the radius is equal to circumference divided by 2 pi. Okay, so we'll substitute that in for the r. All right, so the area with respect to circumference is going to be equal to pi times this squared. All right, and ultimately, with a little bit of algebra, what we're going to get is a c squared on top, circumference squared on top. The denominator is going to be 2 to the second power, which is a 4. You also get a pi squared, but one of those pi's is going to cancel with this one. So we get 4 pi. Example 2. Grain is leaking through a hole in a storage bin at a constant rate of 8 cubic inches per minute. 8 cubic inches per minute. The grain forms a cone-shaped pile on the ground below. As it grows, the height of the cone always remains equal to the radius. This measurement here, the height, is going to be equal to the radius at all times. If the cone is 1 foot tall now, how tall will it be in 1 hour? All right, so you may have noticed I underlined a couple of units previously, inches and minutes. As the pile grows, it's going to increase by 8 cubic inches per minute. But the units that have been provided for us for what we're going to answer are not in those units. It says that the cone is currently 1 foot tall. So what I'm going to do is show that as 12 inches, which would mean that the radius is also 12 inches. In addition, we're going to be asked how tall it is in 1 hour. Okay, in 1 hour. But if our rate is based in minutes, we should be thinking of that as 60 minutes. All right, so what we're going to start with is calculating the volume now and the volume in 1 hour. So the volume formula is going to be V equals 1/3 pi r squared times h. All right, and in this case, the radius and the height are both going to be 12 inches. So right now, let's call this V naught. That would be equal to 1/3 pi, and if you got 12 squared in another 12, that would be 12 cubed. All right, let's go ahead and calculate that volume. We're going to have 1/3 multiplied by pi multiplied by 12 to the third power. which gives us 1,809.6. All right, in 1 hour, the volume's going to increase from here. Okay, so in 1 hour, let's call this V1. We're going to need to take the current volume and we're going to add on to it the amount that it will accumulate over 1 hour. Okay, and that goes back to the 8 cubic inches per minute. Okay, so if we multiply 8 by 60 minutes, that would give us our volume in 1 hour. So let's see what that equals. We'll just go ahead and take that answer plus 8 times 60. So we get 2,289.6. That would also be cubic inches. All right, so for our second part, we're going to think about how we use that. We're going to write a function for the volume in terms of height. We'll then solve for the height, and that'll answer the question. All right, so let's just start with our volume formula in terms of h. V of h is going to be equal to 1/3 pi. It would normally be r squared times h, but r is going to be h, so we get h cubed. Okay, now we know our current volume, which is 2,089.6. So we'll set that equal to 1/3 pi h cubed and solve that. And to solve it, we're going to multiply by 3, divide by pi, then take a cubic root. All right, so we already have our current volume. Multiply that by 3, divide it by pi, go ahead and press enter. And from here, we're going to take a cubic root. Okay, a cubic root of that answer. And we get about 12.98. Which would be inches. Example 3. This might be the most confusing one that we look at. The reason is the description might not be perfect for the diagram that we have. But I'm going to do my best to explain what we're looking at. A small satellite dish is packed with an upright cardboard cylinder inside the dish. The dish is parabolic with 24-inch diameter and 6-inch depth. The diameter of the cardboard cylinder is 12 inches. How tall must the cylinder be to fit in the middle of the dish and be flush with the top of the dish? Okay, so here's the diagram that we get. This is a cross-section of this situation. The satellite dish is parabolic. It's a parabola. You could model it with a quadratic function, which is what we're going to do in a moment. Okay, so there's that cross-section of the satellite dish. Inside of it, you can see this box, what looks like a box, but is actually a cylinder. Okay, the round part of the cylinder is actually going to be up here at the top, also at the bottom. Okay, so it's upright, meaning that if you looked at this from above, you would see the satellite dish perimeter, plus you would also have that cylinder inside of it. The question wants us to figure out how tall the cylinder must be. So the height of the cylinder, that'll be this part here. That's the height. You've got your base up here. You got your base right down there. So that would be the height. How tall must the cylinder be so that it is flush with the top of the parabola? So what we're going to do to answer this question, we're going to build off the fact that this is a parabolic shape. That would be a parabola. And a parabola can be modeled using a quadratic function. Now for conveniency, what we're going to do is draw that cross-section on a coordinate system. And to make everything work out as easy as possible, we're going to put the vertex at the origin. Okay, we're not going to shift it up, down, or left and right. And if we do that, the only transformation that could be applied to the parent function of quadratics, which would be y equals x squared, the only transformation we can apply to that would be a factor, some factor that would stretch it or compress it horizontally. Okay, so our template is going to look like this. It's going to be a factor of a multiplied by x squared. Again, we don't have any translations going on here, so you get a really simple equation. Okay, let's go back to the graph here. You're going to notice there's a couple of points identified. Because the diameter of the satellite dish is 24 inches, this half of it is going to be 12 inches. That is also going to be 12 inches. So we get a couple of coordinates here. The distance out is going to be 12. The height is going to be this height, which is 6. All right, so given these coordinates, whether you use this one or that one, we'll use that because it's positive. You can plug them in for x and y and solve for the a value. Okay, so the y value would be 6. The x would be 12. All right, so a is going to be equal to 6 divided by 12 squared, which is 144. And of course, this is going to reduce, so let's have the calculator do that. We'll take 6 over 144, reduce that fraction to 1/24. So overall, we get this equation. All right, so our job is to figure out the length of that segment right there. And to do that, we're going to compare the height of this point to the height of this point, which that, of course, is 6. Okay, so how to get the height of that? That point sits along the parabola. It has an x value measuring out from here, which would be half of the diameter of the cylinder. And the diameter of the cylinder is 12 inches. So if we go out 6 inches, we're talking about that point right there. All right, so let's take our function and go ahead and plug in 6 for x. That would give you 36. So we got y is equal to 36 divided by 24, which is going to reduce to 3 over 2 using factors of 12, which is the same thing as 1.5. All right, so if the height here is 6 inches and the height here with respect to the x-axis is 1.5, we can take 6, subtract 1.5, and we get 4.5. That would be inches.
Later, blah.